approximating the post-impact behavior of the entire impacting body. And a minimum of 3 points would be required if the surface is a plane, if it's a plane surface, to analyze the post-impact behavior. However, if we are selecting, if we are choosing to go with 3 impact points, this is the minimum for a plane, we also need to find a way to appropriately select these points. In this paper, it has been shown that if these points are not appropriately selected, the impacting bodies actually could penetrate the ground. And so instead of using all this analysis to this additional analysis to select these points, a much better way would be to have have a large number of evenly distributed points and perform an impact analysis on all those points. Now, every time we add additional point for analysis, we are adding additional 3 constraint forces in the equations of motion. And if the number of constraint forces exceeds the number of degrees of freedom, then the impact analysis problem becomes indeterminate, which means we are trying to solve more number of constraint forces with fewer equations. So in order to understand how we can add more and more points and analyze impacts on a surface, we first need to understand how we can resolve indeterminate impact problems.
I can ask questions along the way. Can you go back to the slide? One thing I was never clear, or not clear, is like, what do you mean by the number of degrees of freedom?
So the number of equations of motion. So that would be it's really the dimension of the cube or the generalized coordinates.
Okay, so these are not the x, y, z, and the poles, but you're talking about the joint.
Yeah, joint space. All the joint space coordinates.
Okay. Right, so that's what I was trying to. I could not figure out, like, if you give an example, these are the number of degrees of freedom for an example, and the constraint forces that you're looking at here is this, and where the indeterminate happens.
Yeah, there's a.
Maybe it comes later on, but it was not evident at that moment.
So in the literature, there are 2 main approaches for addressing indeterminate impact problems. One is the continuous or the complying method. In this, essentially the indeterminacy is solved by adding degrees of freedom, and this is done by making the impacting bodies deformable, so that it no longer remains indeterminate. And the other approach is the discrete approach. In the discrete approach, the idea is to stop the simulation whenever a contact is detected, and then restart with some sort of post-impact velocities as the initial conditions. So now, calculating the post-impact velocity, there are like 2 major approaches. One is the iterative approach, and the other one is the analytic approach. In the iterative approach, essentially the constraint forces, which are, if it's an indeterminate system, which are larger than the number of degrees of freedom. In that sort of situation, an optimization methods are used in the iterative approach to solve for the constraint forces, and this is done using some energy-based cost function. And on the other method, which is the analytic methods, the constraint forces are related to each other using certain parameters like coefficient of friction and coefficient of restitution. And in the 2-dimensional case, analytic methods usually converts the whole equation of motion into a simple algebraic equation, and that's why the name comes analytic approach. But however, in the 3-dimensional case, due to discontinuity in the slip direction on the impact plane, this cannot be constructed into a algebraic equation, and we have to use numerical techniques to solve that sort of problem. So in our case, it's a three-dimensional case, so we are sort of close to the analytic methods, but we are using a numerical approach. And these are some of the papers which sort of are representative of different approaches. So the main research contributions in this work are the following. The first one would be to develop a framework for analyzing impacts on using large number of points on impacting bodies while using a discrete simulation approach. Second one would be to show that even if we select more number of points, the result that we get is similar to the base result, which would be to have like the minimum points appropriately selected. And this whole work would actually help us alleviate the need for analyzing that considering the additional analysis on how to select those points. And finally, we have implemented this on a legged robotic model, which is the Atlas robot. So to describe the impact model, I'll first begin with the equations of motion. Over here, A is the inertia matrix, Q double dot, or this Q would be the generalized coordinates, B would be the Coriolis terms, and G would have all the gravity-related terms, F are the constraint forces, and tau would be the actuated torques. So JC is the Jacobian matrix that converts this constraint forces, like the contact constraint forces, in terms of the degrees of freedom. And G is a permutation matrix that just selects the appropriate torques for the appropriate degrees of freedom. So note that the dimension of F would be dependent upon the number of points we select. So in case we select more points and the dimension of F exceeds the dimension of Q, then it becomes an indeterminate problem. So in the event-based approach that we are using, the main idea is to stop the simulation, and there are like two phases. So first there is a pre-impact phase when the impacting bodies are coming into contact, and there's a post-impact phase where the impacting body is leaving contact. And there's a infinitesimally small period of time in between where we are analyzing the impact. So this is what we are calling the impact event. And during this time period, the velocities of the impact body changes to so that to like and reaches the post-impact velocity that is set as an initial condition for the simulation. So so before I begin,
I have a quick question.
Okay.
Can you go back to the previous slide? So the way you have drawn this schematic, so I hope this is not your solutions that you are solving here is limited to us. That means, is this only can solve this problem when it makes a contact in this fashion? The full plane of the bottom surface is making a contact, or it could be any.
It could be any. So I have two simulation results. One for like the collinear case of the central impact, where it's like falling just straight fashion, and the other one.
So it could be statistically any random points that can make the first contact. Is it?
But you still assume a minimum number of points for the problem to be determined.
Yeah.
It cannot be a single point contact, or can it be a single point?
It can be a single point contact. The method.
Think about those very popular bouncing ball things, right? The games, very rudimentary games that we even have screensaver, right? Something impacts on the wall and bounce back and moves around. So that is, in my view, is we can make a comparison to those problems with this one you're solving, because where only thing is that it's one single point, you make an impact and bounce back. It's pure kind of opposing force lead mitigating this, aftermath of this impact, right? How is it different from what you were solving?
So in case of single point contact, we like for example if we are considering a block and if we do a single point contact, we do not know what would be the overall configuration of the how the configuration of the block would evolve. So in case of like a surface, it would be more helpful to have more contact points so that so that we can sort of
So maybe I will have these questions again later. Let's see what you have.
So I'm just going by your motivation when you talk about basically minimum of 3 are required for the plane analysis. So essentially your contribution would be to get rid of that plane analysis.
yeah. So if this method can solve any kind of any number of impact problem like impact problems with any number of points. So we don't need to do that additional analysis to how to select those points because in case like certain configuration, it depends upon the configuration how to select those points because based on how we select the points, there is going to be a center of pressure through which the ground reaction force is going to act through the center of mass. So if that center of that ground reaction force vector is not normal to the plane, it can.
Right. So I understand that. So the only other question I would have on that is how do you know what points have touched the ground?
And that is we will have to do a contact detection where we stop the simulation based on.
In reality, the foot length, right? How do you know which points actually touch the ground? Because in simulation here, you just uniformly distribute the points. So you know exact locations of all the points, so you can solve it. But in an actual scenario, you don't know what points actually did the contact.
There is a possibility of getting those from the feedback from the joints, like the encoder feedbacks. If we know that based on how the joint angles are, we can know like what is the position. We can always track the position of like certain points.
From the joint angle, I don't think you can. You will need a different kind of a sensor, possibly pressure waves or something like that, which can tell you exactly where they are, or a force sensor or something like that.
We can also have some force sensor to detect contact initially.
Because in your write-up, I don't think you address that piece.
That's out of his scope.
Because I know it is out of the scope, but my point is like this is fine as an analysis, but that is a practical problem, right? In simulation, it's fine, everything is under your control, but in a realistic scenario, that is the biggest challenge for is to detect which points you actually touched on the ground. And you can write a little sentence there saying that you are assuming some sensors are available that tell you, at least with reasonable accuracy, what points hit the ground. Okay? And once that is known, then everything comes in your, so you have the machinery to run through the whole thing. Don't open up that kind of a question. You just touch your base and cover it up. Because then people get sidetracked along the way.
So here are a few assumptions that we have made all through this work. All the bodies are assumed to be rigid, so there's no relative velocity or relative motion between different points on the body. And there's also no change in configuration during impact, which means the generalized coordinates during the impact would remain constant. Finally, contacts are assumed to be a series of impacts, and after a while it would be terminated based on if the post-impact velocities reaches like with since this impact event occurs over such a small period of time, uh, generally in the equations of motion, the generalized accelerations and the constraint forces become very large during that time. And so, and to in order to simulate that in a continuous fashion, we had to reduce the time scale to like very small. So instead of doing that, much better way would be to convert the whole equation of motion in terms of an impulse velocity relationship, and that could be done by integrating the equation of motion over the small period of time. And then note that we said that the q remains constant, so which and also the q, that means the q dot would have a bounded value during that time. So essentially, the Coriolis terms and the gravity related terms, which are just function of q and q dot and q, these are going to be bounded. And when we integrate it over a very small period of time, these are going to be negligible. Similarly, goes with the same thing goes with the torques, because the torques are going to be bounded. Actually, the torques are going to be bounded. We can neglect that.
So
However,
V here is that JC times Q or something like that, right?
this
The
one,
V here, Q dot, JC times Q dot.
yeah.
Okay.
So once, but like q double dot and force, these are not bounded. So when we integrate that over infinitesimally small period of time, we get a finite value, or the integration will be bounded. And we can just multiply a Jacobian matrix on both sides while inverting the inertia matrix to get the velocity and the impulse relationship. So at this point, so essentially what we would try to do is to find this impulse that occurs over the impact event. And we need to find the impulse in such a way that the whole system is energetically consistent, which means that the energy, the change in energy after impact should decrease and not increase. So, and now to incorporate that an energetically consistent way of selecting those impulses, what we first need to do is to reduce this whole equation 3 in terms of one independent variable, so that we could eventually evolve it as a function of impulse and get to some post-impact velocity. And so firstly, we could begin by relating all the tangential impulses in terms of the normal impulses using Coulomb's friction. And equation 4 gives how the Coulomb's friction force could be written in terms of impulses. And equation 5, where we can see matrix H, which is just a transformation matrix from the tangential from the normal to the tangential. So in equation 5, we have reduced all the contact point velocities in terms of the normal impulses. And now we still have different points, normal impulses at different points. So the next thing would be to relate those different normal impulses in terms of each other. And that could be done using the rigid body constraint assumption that we had made earlier. So in the rigid body constraint assumption, we say that the velocity, or we say the different contact points, different points within a body do not move relative to each other. So the velocity, relative velocity of these points would be 0, and that could be described using this constraint equation, velocity constraint equation. And this paper, it describes a method for converting such a velocity constraint equation in terms of impulses. So if we can convert this velocity constraint equation in terms of an impulse constraint equation. So once we do that, we could relate the different normal impulses in terms of each other using some coefficients like CQR over there. And then once we have the set of CQRs, which are the coefficients for rigid body constraint coefficients, we can put that all in a vector and describe all the velocities in the system, all the velocities of the contact points in terms of one independent variable impulse. At this point, I would also say there's since there is this discontinuity in the slip direction on the impact plane, and we actually have to do an event-based integration for that, which I'm not going over because it's prior work. And so for that kind of situation, we have to do. We would essentially try to describe all the velocity in terms of cylindrical coordinates. And P inverse over there is a transformation matrix that converts the Cartesian coordinate velocities in terms of cylindrical coordinate velocities. And then at this point, if we evolve the velocities with respect to like impulses, we would be able to get a plot like this, where S is the sliding direction, sliding velocity, phi are the sliding direction, and Vn are the normal directions, normal velocities.
Hard to see on the picture what it's really.
So the green is the sliding direction, red is the sliding velocity, and black is the normal velocity. So you can see the normal velocity goes from negative to positive during the
You want to get a movie?
huh?
You're trying to get a movie on it.
For some reason, the plot is not showing up. I don't know. So so next we are trying to get basically in the previous slide, as I explained, we can reduce all the velocity in terms of one independent impulse, normal impulse. So next we will have to find how to compute that normal impulse over the impact event, and that could be done using the energy dissipation, sort of setting how much energy we want the system to lose during the impact. So typically, all the energy loss in a system during impact would be captured in the normal work during the impact, and the normal work would typically have this characteristic parabolic equation, and that is because in this case it's a network, and since we have the velocities which are being multiplied twice, it becomes so this is like the post-impact velocity and the pre-impact velocity. Since it's being multiplied twice, and if we substitute all the equations where we are relating the velocities in terms of the impulses, we get a parabolic equation with respect to the impulse, how the work evolves. And so then we can get a normal work equation, which is a function of the velocities and the normal impulses. And before that, in this parabolic equation, this is the point where so this part before the vertex is the compression phase, and this part after the vertex would be the restitution phase. So in a in a deformable body, the compression phase would be when the maximum deformation occurs, the phase where the maximum deformation occurs. And restitution phase would be when the body regains its full shape. So, and we would expect an energy loss when the body regains its full shape. So, at the end of the compression phase, that is where the normal work would be minimum, and we can find this end of restitution phase based on what we get as the end of compression phase. Okay. So we can write the equation for normal work in terms of velocity and impulses, and then we can find the compression phase, the end of compression phase, by checking where the rate of change of work, normal work with respect to impulse becomes 0. So that would be the end of the compression phase. So we can find end of compression phase work, that is WNC over here, and then we can use constant coefficient, not constant coefficient, and energetic coefficient to find what would be the end of restitution phase normal work. So that is where the impact event should end. So what we would do is, from this point is, we would keep evolving the velocity, and when the normal work reaches this value, we would stop the, that would be our, so whatever velocity we get at that point, that would be the post-impact velocities to restart the simulation for.
So in this, how do you choose this epsilon, basically the impact event time? I believe it is about 0.2 in this normalized form. Or just describe how you choose the epsilon.
This one, sorry, the coefficient of restitution.
Yeah, go back. Yeah, this equation, that is t plus epsilon, that is the time for the impact event, right?
Mm-hmm.
So how do you choose that?
So we don't compute this at all. We are just doing a algebraic derivation from this to end up here. So in a real simulation, we wouldn't stop the simulation during that for any epsilon period of time. We would just because it's infinitesimally small, we could just compute the post-impact velocity based on like whatever algebraic equations we have.
So you don't make any choice for epsilon.
So the rationale is basically you detect impact, and in simulation, when you detect that event, then there are a set of algebraic equations you will solve, and you will get the post-impact velocities. So in simulation, then all the velocities have changed. Very continuous.
Please don't do that. So is
That's not the answer.
I mean, that's part of the answer, but the solid answer is, you wrote that equation in terms of time. Is this a time analysis?
So we are converting the whole equation in terms of impulses. So since we are not doing it, the integration with respect to time, we don't need to consider it. So we can just have what would be the change of impulse within that, and we can reset the initial condition based on it.
Yeah, so I got a little curious because with a similar analogy, a problem I solve, related to viscoelasticity of materials, especially when you have some kind of shear transfer occurs. We solve a time and space dependent solutions, but considering only space, not time, exactly like what you are doing. And then with our parameter that we vary there, incorporating time is the rate of loading. So here, let's say you are considering an impact, and if your impact rate changes, then that should affect this epsilon, right? To some extent, isn't it?
Well, I mean, if we are doing it in terms of doing the integration in terms of time, it would have an effect, but
No, maybe let me ask this question in a different way. You are just solving this robot having a walk, right? How the solution will be different if the robot runs or slowly walks? Would that be a different, or it will be exactly the same solution?
so if a robot is running, so the pre-impact velocities, the velocities that we were considering before, would be higher, whereas as compared to if something is walking. So based on that, the loss of energy and the impulses over there. I mean, in the in actual in case of, so rigidity is like an idealization, but in a deformable case, there would probably be a difference between how much something deforms.
No, I think deformation we don't need to consider. That is fine.
Yeah.
You're assuming this is rigid body, that is okay. Only thing this is a curious question. Maybe this is not my field. I do not really go through the details of this solution perspective. But from practical point of view, a robot may need to go faster or slower. It may need to jump. Different scenario may happen. Would your solution be different
Yeah.
if those scenarios happen?
Yeah.
And what would be the parameters that would be affected so that your solutions will be different?
So
That's what I want to know.
So the main point over here is the energetic coefficient of restriction. So that dictates how much loss of energy there would be, and over here we are considering it to be a constant, and we are simulating for different cases. But ideally, what we would like to do is we would need this to be a variable in terms of what the initial velocity is. So in case, like, let's say a robot is running where the initial velocity is like higher, then there would be higher energy loss. Whereas if a robot is like walking with a smaller initial velocity, there would be less energy loss during that time. So in this.
But those initial velocity that we're talking about is kind of the whole global velocity of the robot, right? That going, let's say, parallel to the surface.
No,
where it
velocity
is,
of the
right?
contact points. So that is what is important over here, because that determines what our energy loss would be. Because from a deformable point of view, it's really that the points are that parts of the body are deforming, and because of the elasticity, that's where the energy is lost.
No, I'm not talking about that part. Only thing I'm concerned here, let's say if something goes fast or slow, only thing that will be different is how long it stays on the ground in each leap, right?
Yeah.
If it walks slowly, that will be longer duration stay, and if it is not slow, it will be very short stay.
Okay, I see what you're saying.
So how do you bring this parameter into your solution, or are you bringing this parameter into your solution? That is what I'm asking.
So for example, like I said, assumption before, like where we are saying that the contact would be a series of impacts. So we are not adding that parameter into the solution. That's why we are looking for contact means where the epsilon would be large, right? So in that kind of situation, we are looking at it as a series of impacts. So it would go up and down during that time, the velocities. So that's
There's a better answer.
Okay, so I think you
Let's come back.
Okay, yeah.
Let's come back to that.
So I have
I
some.
think he knows the answer. I'm not saying.
Okay.
I'm not saying. But go ahead.
I have some simulation of the blocks. So this is a collinear impact where we are just dropping the block flat on the ground. And so this is the 4-point case and this is the 8-point case. And we can see almost very similar behavior in both cases from the animation. And now when we look at the velocity plots, we see the so the initial velocity should be the same because it's being dropped from the same height. And but like the final normal velocities, these two, these are almost exactly same in both cases, and
You keep saying they're almost exactly the same. Are they the same? Are they exactly the same, or they're not exactly the same?
it looks exactly same from the plots. I don't know the exact values, but it looks very close to each other. And so since it's been dropped in like a straight configuration, and there is no sticking or so it's actually sticking all through the impact. So that's why the sliding velocity and the phi, which is the sliding direction, remains zero throughout the event. And since we have so this in this case we have 4 different plots for velocity for each of these cases, and in this one we have 8 different plots, but they are all overlaid on each other because it's coming straight down and straight up. And then again we look at the normal work. So we can see again the end of restitution work is about -40, and over there also it's about -40. But also note in both cases the impulses. So over here, so this is 5 and this is 10. So in this being the 8-point case, we can explain that how the impulses are less because we are selecting more number of points, so the impulses are getting distributed equally. And since in this case, like this is 4 and this is 8, so it becomes half the impulse.
We had an odd point in this case.
Hmm?
The line is not aligned with the 10.
Yeah.
It looks like 10 and a half, and the watery planet.
I'm not looking for exactly.
Practical line, right?
So this is a collinear case, and sorry, this is a non-collinear case, and we can actually see the block switching contacts, and this is what we call rocking block. So first and it actually goes through many different impacts, but I'm going to show the velocity at the work plots for only the first 2 because the rest are similar. So in this case, this is 4 point and 8 points, and again we see the impulses are getting reduced in this case, and velocity is around post impact velocity. So magenta are all the normal velocities, and these are coming out to be exactly similar value. And this is the work plot. So we see around -8, and this is also about just slightly lower than -8 in both cases. So and this is like second impact, and again we see the normal velocity is almost same in all cases, and over here this is an extra that is one of the other additional points. Since it's rocking, it's not overlaid on each other, so we are getting to see an additional point over there for the normal. And also for the work plot, again we see around -10 over here and around -10 over there. And the normal impulse gets reduced in the 8-point case. So now I'll show the example with the bipedal walking. So this is a simulation for this is the 4-point and 8-point, and over here we can see the impulses that are occurring during that time, and it looks like it's not possible to decipher exactly what is happening, but it's like a very similar behavior in both cases. And so finally, I would conclude by summarizing what we have really found found through this work. So this work firstly presents a framework for analyzing large number of impacts, on surface impacts during impacting bodies, and this also shows that analyzing more number of points yields similar results as the minimum number of points if selected properly. And basically this is, so over here I've shown like 4-point and 8-point cases, but this method we believe could be extended to larger number of points. So we can have like a mesh or a grid of points on impacting bodies, and we could get accurate results after the impact event. So finally, I would like to acknowledge Dr. Bowling, who's been my advisor, committee members, Dr. Adnan and Subara for their interest, my colleagues, past and current colleagues, and friend Philip Bailey, who will be flexible. Questions?
Does the audience have any questions on this? They don't see this thing 3-4 times. Any questions?
No, I don't have any.